In this part of chemistry, we are going to talk about several points that are related to reactions, heat, gases, and enthalpy. The first point is, what is the difference between limiting reactant and leftover reactant? Okay, for example, now if I have 7 moles of Na and I have 10 moles of chlorine, and I want to make reaction that is with sodium and chlorine, as we know it will give us what? NaCl. Okay, so that means here, it means 1 mole of sodium with 1 mole of chlorine. When they react, they will give us 1 mole of sodium chloride. Okay. If I have now 7 moles of sodium and 10 moles of chlorine now, and I want to react them, which of them will finish first? Which one will be finished first? Of course, sodium. So that means now, if I have here 7 sodium, they react with 7 chlorine, and they'll give us what? 7 NaCl, which is sodium chloride. Good. In this case, when this reaction has been finished here, will I still have sodium, or all of it used in the reaction? All of it used, 7 moles of sodium. So that means this one finished. But what about this one here on the other side? All of it finished? No. 3 moles is still there. 3 moles is still there. So in this case now, which one of these 2 elements, which one was the controller of the reaction? That means which element that stops now the reaction and no more can the reaction take place. So that means it's the sodium because it finishes first. So that means this factor now we call it limiting reactant. Limiting reactant. Why? Because it will give you what? The limits of the reaction. And this one now we call it what? Leftover reactant or excess reactant. Okay, so that means now if you want to define now the definition of limiting reactant, what is it? It is the reactant that is consumed completely in the reaction. Again, what about this one now on the other side? It is the reactant that is not consumed completely in the reaction, but there is still a quantity that is not used. So you understand now the first point of this part, which is the difference between limiting reactant and leftover or excess reactant. Good. We'll go to the second point now. In the second point, we're going to talk about actual yield, theoretical yield, and percent yield. Okay, and what's the difference? As we know, when we make reactions now and we calculate element X reacts with element Y, it gives us XY, and it gives us, for example, like 3 kilojoules heat. For example, in this case now, this is now when we make a reaction like this now, and we use calculations and we understand what it's going to give us here, and how many moles of these ones will react, and how many moles of this will react, and how many grams of products we will get. This one is calculations, but this reaction, when we conduct this reaction by experiment in the reality, will it give us the same numbers? No, because there will be waste of particles, waste of reactants, waste of or additional reactions, not just this pure reaction happens. So do these other factors now, these numbers will be changed, but not that change. They're gonna be changed by a smaller percentage, For example, now I give you example. If we make calculations, and you found that 100 grams, 100 grams of a product we will get. By calculations, for example, now of a reaction, we calculated and we found that we'll get 100 grams of a product. Good. Then when you conduct this reaction by experiments and the reality, we found that only 92 grams are found in reality. So this number now, we call it theoretical what? We call it what? Theoretical yield. And this one we call it what? Actual. This one we call it what? Actual yield. So that means theoretical yield, it is the maximum number possible that we'll get due to what? Calculations, theoretical calculations. That means it's not experiment. And the actual yield here is the number that, or the actual number that we will get by conducting the reaction on reality. So you understand now what is theoretical yield, and you understand now what is what? Actual what? Yield. Good. Okay, now, if we are talking about a third concept here, which is percent what? Yield. What is percent yield? Percent yield equals the actual over what? The theoretical. Over the theoretical. So in this case now, what will be the percent yield in this question? It's going to be the actual, that is 92, over what? Over 100. Then you multiply it by 100, just take it what? As a percentage, you will find it 92%. That means now 90% of the theoretical calculations, we will find it in reality, 90%. That means there will be a waste of 898% that is not found in reality. Okay, so this was the second point of this part. Okay, you'll go to the third point now, which is molecular kinetic theory. Molecular kinetic theory. So molecular kinetic theory of gases, it is just designed for gases. So that means it is called molecular kinetic what? Theory of gases. Of what? Of gases. Okay. This molecular theory states or focuses in about main points here. The first point, it says that gases are particles that are tiny, or gases are tiny what? Particles. Good. This is the first point. Okay, this point. It is talking about the distance, the distance between the gases particles. It says the distance between gases particles is huge compared to their size. Compared to what? To their size. Okay, what about the third point? It is talking about the movement. It says that gases are moving in random, constant, straight line motion. Good. So this is the third point. Fourth point, it is talking about when these gases collide, they collide elastically. That means they don't lose energy before or after collision. And this molecular kinetic theory of gases, mainly it is based on what? On the movement. So that means the principle or the base that it depends on giving these assumptions, it's mainly about what? The movement of gases or of particles. Not all these things, by the way, are real on gases. Some of them are right for ideal gas particles and some of them for real gas particles, and there is what? A difference. Like for example, the difference between ideal gas and real gas. Ideal gases, just we assume that there are ideal gases, and there is the attraction or the repulsion between them is about zero. Is about what? Zero. There is no repulsion, no attraction between the particles of gas. So this is ideal gas, but real gases, we have attraction between these molecules. And if we increase the temperature and decrease the pressure, in this case, we can find some, or with this property of gases, we can find it for real gas, the same like for ideal gas. Okay, this is the third point for this topic of today. Okay, what is the fourth point? The fourth point will be about, or just we'll extend this point, which is the third point. If we are talking about just gases now, we're going to talk about what is diffusion of gas and what is flow of gas and what is expansion or compression of what? Of gases. Okay, diffusion of gas. Diffusion of gas is when the gas particles move from higher concentration to lower concentration. How? For example, now, if someone is in the kitchen in your home now, and you are in your bedroom, good. If someone is cooking there, you can smile. What is she or he cooking? Good. In this case now, what came from the kitchen to your bedroom? What comes? The particles of the food itself, when it was changed, when they were changed into gases, they moved from the higher concentration of these particles. So these particles are highly concentrated in the kitchen now. So they moved from the kitchen into what? Your bedroom. And this movement now we call it diffusion of gases. We call it what? Diffusion of gases. Okay, what about flow of gases? Flow of gases, if you have a container or a pipe, so that means if you have a hole that gases move from or gets when gases get out of this hole, or they move through a pipe, in this case we call it what? The flow of gases. So that means it's pipes and holes mainly. It's not just related from higher to lower what? Concentration. Okay, expansion, if you have like a container here and you have gases inside it and you expand, that means you enlarge this container, you see this, the distance between these particles of gases becomes larger. In this case we call it expansion of gas. And the opposite for what? For compression. That means if you compress this container, you reduce its size, you're going to see the distance between the particles of the gas becomes smaller. In this case, we call it what? Compression of gases. And there is here a formula here that is related to diffusion of gases, which is Graham's law. Graham's law says the rate of diffusion of gas, the rate of diffusion. For example, as I said, the gases now are coming from the kitchen into your bedroom. And the gases are of different atoms, of different elements, right? When they come to your bedroom, they represent different elements of the food that is cooked. Good. The rate of diffusion, that means like which one goes faster, which one goes slower. The rate of diffusion here, it is inversely proportional. So that means the rate of diffusion is inversely proportional to the molar mass of the element or of the molecule. So that means if I have two gases now are diffused from one room to another room or from one area to another area, in this case, the rate of diffusion for the first element over the rate of diffusion of the second element, it equals the molar mass here, molar mass of the second over what? Molar mass of what? Of the first. Okay, so that means this relationship is inversely proportional. Here you'll find the first one, here you find the first one, you see? So that means one in the denominator on the right and one in the numerator on the left. In this case, we call it what? Inverse relationship. This one is called Graham's law. And any two elements or two molecules, as long as they have the same molar mass, that means their rate of diffusion will be the same. Look, molar mass, it is the, for example, if you see the periodic table, you'll find that helium, it has a mass 1 on the periodic table. And 1 here, it represents also the molar mass, which is, molar mass, it means it means the mass of 1 mole of this element in grams. How many grams is the mass of this element in what? In 1 mole only. What is the mass of 1 mole of this element in grams? This one represents the molar mass. And if you have H2O and you want to find its molar mass, the hydrogen, its molar mass is 1. So you have here 2 hydrogens, so 2. And the oxygen, it has 16 molar mass. So that means 16 here plus 2 for hydrogen. So that means Here now the molar mass is what? Is 18. For water, when it is like what? Like a molecule. So that means in this case, if you have a water gas and any other gas, and you want to see which one has higher rate of diffusion, you're going to see what? The one that has less molar mass, that means it's lighter. So that means its rate of diffusion is greater. Okay, related to the fourth point, which is gas pressure. If we have now in our room here, for example, we have three types of gases. We have hydrogen, and you have oxygen, and you have nitrogen, for example. They'll make a mixture. Yes, this is mixture now, a mixture of gases. They'll make a pressure between themselves and the wall in the room. Okay, this pressure now represents what? So the total pressure of gases in a container, it equals the sum of the partial gas pressure. So that means here, if I want to get the total pressure of these gases, I'll find the partial pressure of hydrogen and the partial pressure of oxygen and the partial pressure of nitrogen. In this case, when I find the sum, it represents what? The total pressure of the gases that are in this container. And this is what is called Dalton's law of pressure, or of gases pressure. And if the room or of these gases are in the same temperature, their partial pressure will depend mainly on their concentration. Will depend mainly on what? On their concentration. So that means the higher concentration will have the higher pressure if they have the same temperature. And for pressure, we have two devices. We have barometer and we have what? Manometer. We have manometer. Barometer is a device that is used to measure the atmospheric pressure, while manometer is the device that we use to measure pressure in closed containers. Now we'll go to the fifth point, which is related to chemical potential energy, heat, and enthalpy. Okay, what is chemical potential energy? Chemical potential energy is the energy stored in a substance due to its composition. That means, like for example, now when you have benzene that we use for our cars, this benzene that we use for our cars now, it gives us energy, it gives the car energy in order to move. Okay, what types of energy were or was stored inside this chemical substance? So the benzene is like a chemical, it has a chemical energy stored inside its composition due to its bonds and the number of molecules or number of atoms inside. So as a result of this composition of molecules and bonds, this composition, it has chemical potential energy. And after this chemical potential energy in the car is burnt, it changed into thermal energy. And then thermal energy with the engine of the car, it is changed or converted into mechanical energy, so the car moves. So what is chemical potential energy? It is the energy stored in a substance due to its composition. And it's not the energy that is stored in the nucleus, because this one is related to the nuclear energy. And this energy is different from the thermal energy, because thermal energy is related to moving particles, and thermal energy is the sum of the kinetic energy of moving particles. So that means if you have particles here and you heat them, that means you are increasing their movement. When their movement is increases, their speed increases. And the sum of this kinetic energy of the whole particles, of all the particles, is called what? Thermal energy. But if you are talking about just one specific particle or one specific object, and it is moving, and you're talking about its energy, in this case, you are talking about kinetic energy, not thermal energy. So you understand the difference between thermal energy, kinetic energy, and also chemical energy. Okay, what is heat? Heat is also type of energy. Get type of energy. When it is transformed from one object to another object, this heat now, which is thermal energy, when it is transformed at this point only, we call it heat. So the heat is related to transformation. When it is moving from an object to another object, from warmer or hotter objects to colder objects, this energy that is being moved, we call it what? Heat. Good. But if it is not moving, if it is just inside this one stored as heat, we call it what? Enthalpy. We call it enthalpy. And heat in general, as it is type of energy, we have two units to measure or to use it in as a unit of heat. One of them is joule and one of them is what? Calorie. Okay, but we need to understand the difference between three things. One of them is calorie, which is C small, A small, as you see in L, and one of them is calorie with capital C, and also what? Joule. And what's the difference between them? To understand the difference here, you need to remember here that 1 calorie, one small calorie, it equals 4.18 or joule. So that means one small calorie, it is about 4.18 joule. Good. What about this big calorie when it has capital C? This one here, it means kilo small calorie. That means this one now, it means 1,000 calorie. So when they tell you change or convert from calorie to joule, you need to understand what calorie they are talking about. Okay, if we are talking about 1 calorie, but here now, big C, capital C, 1 calorie here. If you want to convert it into joules, what are you going to do here in this case? We'll multiply it now times 1,000 in order to change it to small calorie. So that means it is what? 1,000 small what? Calorie. Good. This is the first step. Now we're going to multiply this 1,000 calorie times 4.18 in order to change it into what? Into joule. We'll find it that is about 4,184 joule. So you understand now how to change or how to convert calorie with a small c to calorie, the capital C, into joules, and the difference between them, and all of them units of heat or of energy. And in general, the device that we use it to understand how many calories are there in an object and in a molecule, we use what is called calorie meter. And it tells us, for example, how many calories in a piece of chocolate or in a part of a chicken or a meat or whatever. We use calorimeter to tell us how many calories. That means how many energy in numbers in that part that we want to measure it. Okay, we understand now heat, thermal energy, chemical energy, and what's the relationship between them. Okay, this point now also we're going to talk about what is enthalpy. What is enthalpy? Okay, what is enthalpy? Enthalpy is also energy, and it is heat content that is stored in an object. But it's not related to its composition or not related to its composition, just it is the energy that is stored in an object. Good. As heat, by the way, and it is heat content called. Okay, this enthalpy, by the way, which is H. Sometimes we have a change in enthalpy. How? If we have a reaction, that means you have a change in enthalpy. How? The change in enthalpy, by the way, and here we write Rxn, which is a change in enthalpy of a reaction. It equals the enthalpy of products minus the enthalpy of what? Of reactants. Good. So to understand now change in enthalpy, we'll have, as we know, exothermic reaction, and we have what? Endothermic reaction. So exothermic reaction, this is its, this is now energy, and this is what? Time. So it goes from here like this, here. So in this case, this part here is the part of reactants, and here the part of what? Of products. And as you see here now, the energy here is the energy of reactants, and here the energy of what? Of products. So which one is higher energy, reactants or products? As you see, reactants has higher energy than what? Than products. In this case, this reaction is exothermic. So that means it needs to give out energy in order to lower the energy of the reactant to be like what? The energy of products. And in this case, as is here, we said H of products is less than enthalpy of what? Of reactants. And in this case now, if we use it here, which one will be higher? As you see, reactants will be higher. Reactants will be higher. When reactants here will be higher, that means the negative sign here will be greater. So that means in this case, the change in enthalpy of the reaction will become what? Negative sign. Okay, what about the other side here? If we'll go to do it on the other side here, this is now the reaction, and this is, as you see, energy, and here is what? Time. And this is how is the graph of the reaction. Here are the reactants, and here are the products. And as you see here, the energy here is for the reactants, and the energy here is what? For the products. So which one is higher energy? Higher energy means higher point on Y axis, not X axis. So that means, as you see, the products has higher energy compared to the reactants. So in this case, this reaction is endothermic. Endothermic, that means it needs heat in order to take place. When it takes heat, why? To increase the enthalpy of its reactants to be like what? To be the products. This one is endothermic. And since the products now, as you see, so that means the enthalpy of the products is greater than the enthalpy of what? Of reactants. So in this case now, if you apply big numbers and small numbers here in this equation, what will you find? You'll find this part is greater. When this part is greater, minus a smaller quantity, so big quantity minus a smaller quantity will become the big, so that means the positive. So that means the positive will become here, so the sign will be positive. So the change in enthalpy of reaction will become positive if it is what? Endothermic. So remember that when the reaction takes in energy, this is endothermic, and its a change enthalpy will be positive sign. And in this case, the products will have higher energy than the reactants. And if it is exothermic, it releases energy because its reactants has higher energy than what? Than the products. So in this case, it gives out energy to lower the energy the system has. And this case, we call it what? Exothermic reaction. And the sign of the change in enthalpy will become negative. So as you see now, what is the change in enthalpy? It is the change in what? In the heat content in the reaction from when it transformed from reactants into products. All this reaction now, what is the change in the heat? The change in the heat content, it's going to be what? The heat content of the products minus the heat content of the reactants, in this case to find the change in the enthalpy. And we have just some types or examples of endothermic and exothermic reactions. For exothermic here, we have like a hot pack. Hot pack that sometimes people use it in order to get more heat. Okay, it's like cold pack, but this is hot pack. And also we have what? Combustion reaction. So these ones now are two examples of exothermic reaction. In combustion, when an element or a molecule reacts with oxygen, like burning. When you burn something, that means this reaction is combustion, so it gives you heat. So if we are close to a fire, you will get heat. So because this system now releases heat because it is exothermic. And exothermic or endothermic, the system decides, not you. The system decides if it loses heat, it calls itself what? Exothermic. If it takes in heat, it calls itself what? Endothermic. So that means when you are close to a fire, you get heat. But what decides, not you, what decides is the system. So the system, which is the reaction, where the reaction takes place, it decides that it gives you heat. It gives out heat, so this is exothermic. And here we have also cold pack as well as example. Cold pack, if you have a fever or you need parts of your skin to be colder, you put this cold pack or ice pack into your skin. And what happens here? Do you get coldness? What do you get exactly? The heat of your skin is absorbed into the system of that cold pack, into the system of that cold pack. So that means this reaction is endothermic because the system itself has taken the heat from your skin. So this is cold pack, or it is called cold compress. And also we have another example, which is what? Decomposition. Decomposition, most of them, by the way, decomposition reactions is also what? Is also endothermic reactions. And in cold packs, sometimes we put, in some cold packs, we put inside them ammonium nitrate sometimes, and this one we put them as a substance inside this one, since when it makes reaction, its reaction is endothermic, so it takes heat from outside into the system itself. And this is what is also called what? Cold pack. So you understand the difference between exothermic and endothermic, and we understand when the enthalpy or the change in enthalpy will be positive and when it becomes what? Negative. And he said the enthalpy change is going to be positive if the reaction is endothermic, and it will be negative if the reaction is what? Is exothermic. And you have taken examples of exothermic and endothermic. Okay, we'll go now to about the last 2 points of this part, which is a state, a change, and Hess law. This one is the last 2 points. Okay, if I have one mole only of a substance X, good. And this mole is liquid substance, and I want to evaporate this mole to become what? Gas. So in this case, I'll give it heat or I'll take out of it heat. I'll give it heat. Good. When I give this 1 mole of a substance heat, is it called now endothermic or exothermic? Again, the system decides, not you. So 1 mole here, it will take the heat in order to be converted from liquid into gas. So that means this reaction is endothermic, and it is called what? Vaporization. So vaporization, by the way, it is endothermic reaction. So it takes in energy in order to change or to be converted from liquid into gas. Good. So what is the energy now that we need to give this 1 mole of a substance to change it from liquid to gas? This one is called molar heat of vaporization. We call it what? Molar heat of vaporization. And it is called like this here. We can write it this way. So when we write this one here, it means what? It means molar heat of vaporization. So whatever is the number, will it be positive or negative? It will be what? Positive number. It will be positive number. Why it will be positive? Because this one is endothermic reaction. So that means if I have 3 moles, for example now, if this 1 mole of a substance X takes 3 joules, takes what? 3 joules of energy or of heat to be converted from liquid to gas. This one is called molar heat of vaporization. Okay, if I have 2 moles of this substance, it will take twice this molar heat, so it will take 6 joules to change or to convert 2 moles from liquid to gas. Okay, same thing, by the way, same thing, same idea for condensation. So for condensation, if we have 1 mole of gas, 1 mole of gas, and we need to convert this 1 mole of gas to be liquid, this process or this change of state, we call it what? We call it condensation. Okay, in this case, when we convert it from gas into liquid, will it be exothermic or endothermic? It is exactly the opposite of what? Of vaporization. So vaporization, it is the change from liquid to gas, and the opposite exactly from gas to liquid is called what? Condensation. And since that one was endothermic, so this one will be exothermic, and it's gonna be what? Negative. And what will be its definition now? It is 1, or the energy required to change 1 mole of a substance from gas into liquid. And this reaction is exothermic. Okay, you have other ones, by the way, same idea. If we have here fusion or melting, which is molar heat of fusion or of melting. This one now, its definition is what? To change from what to what? Melting or fusion is to change from solid to liquid, is to change from solid to liquid. Good, when I change from solid to liquid, will this system will it need heat or it gives out heat? It needs heat. So that means this is endothermic, and this endothermic will be what? Positive. And if you give it now a definition, what is the molar heat of fusion? You're going to define it as the heat required to convert 1 mole of a substance from solid into liquid. I'm talking about 1 mole, so that means this is molar. And you find the molar, that means you can find, now you can convert for any number given of moles, you multiply it by this number. And also we have combustion as well. We have same thing here for combustion. And also we have for freezing, or you call it what? Solidification. But what will be their definitions? This definition now for combustion, by the way, combustion, it's the reaction with oxygen. And we said it always gives out heat. Any reaction with oxygen, it's like burning something. You burn something. This is combustion. And it usually gives out heat. And that means this is a negative, which is exothermic. And here, solidification, that means if you want to change from liquid into gas, into solid, from liquid to solid. So that means in this case now you give it heat, or it will give out heat. It will give out heat. So that means in this case it will also be what? negative, which is what? Exothermic. As long as it is molar, so you define it the amount of heat needed to convert from this state to the state for 1 mole only of a substance. So you understand here the changes and whether they are exothermic or endothermic and their molar heat related. Okay, what is Hess law? And this is the last point. What is Hess law? Hess law, by the way, it says the change in enthalpy for any reaction, it depends mainly on the type of reactants and the type of products, regardless of the steps of the reaction. So that means it just depends on the type of reactants and the final products, regardless of how many steps. Because in reactions, some reactions, they take just one step. They take just one step and they are changed from reactants into products. While other chemical reactions, they make one step to make it from reactant to products number 1. Then these products 1, they're going to change into products 2, then products 2, they're going to change to be into the final what? The final product. So they take sometimes 3 to 4 steps or 3 to 4 reactions. So in this case now, Hess means the change in enthalpy depends just on the reactants and the final what? Products, regardless of these steps. And it is mainly the change in enthalpy. It equals the sum of the product's enthalpy minus the sum of the reactants enthalpy. So that means even if I have 3 steps, reaction 1, reaction 2, reaction 3, and this is the previous reactants and these ones are the final. So we have here, as you see, reactions here, the sum of these ones, which is products minus the sum of enthalpy of the reactants, will give you that the change in enthalpy of the reaction. And Hess law is used to find the change in enthalpy for very slow reactions, for the reactions that are very slow, or the reactions that we find it very hard to measure its enthalpy. And you'll have examples to solve them. Just you need to remember also something, that we have something that is called standard enthalpy of formation. Of what? Of formation. And for elements in their standard states, for example, now hydrogen is gas. What is the standard enthalpy of formation of hydrogen when it is gas? We say here it is what? 0. And remember that the enthalpy, the change, or the standard enthalpy of formation for any element in its standard state is 0. And this one now we use it also in compounds. If we have like oxygen plus hydrogen, it gives us here water, by the way. And we find something called here, if we just after we balance this one, after we balance it here, if we're going to find the standard enthalpy of formation of water, it equals what? These ones, of formation of water minus these ones. And these ones will be 0. So that means just we find it here. That is the formation or the standard enthalpy of formation of this product or of this compound. And we use that, or you find that by experiments. By experiments, when we make experiments for oxygen, hydrogen, when we burn hydrogen, like we take a quantity of hydrogen or 1 mole of hydrogen, and we put it inside a calorimeter and we burn it, for example, and you're going to see the heat change, the change of heat, in this case, to make 1 mole of the product, which is H2O of this compound. In this case, we call this one the standard enthalpy of formation of water compound. I hope you understand all the steps that are related, which is related to limiting and leftover reactants, and you understand the difference between actual and theoretical and percent yields, and you understand what is molecular kinetic theory of gases, and you understand gas pressure and Graham's law and Dalton's law, and you understand also what is chemical potential energy, and you understand also the difference between exothermic and endothermic and enthalpy and heat, and also his law. Thank you. See you in other videos. Bye.